Thanks everyone for coming. So Ted and I kind of just figured out we would do a meetup, just kind of sharing the interesting stuff that we've been reading and share it with everyone, give simple summaries and just kind of walk through, here's interesting things that's going on, here's whatever we're working on. So I have one that's recent and one that's kind of old, just based on projects I'm working on and stuff I'm kind of studying. And so I figured I would summarize this and share it with everyone. So the first paper is this PDFTriage. So I saw it floating around Twitter and LinkedIn, and everyone was talking about this. So I just wanted to dive in and understand what it's about. I do a lot of work with documents. I work on the document AI team at my company. So it's important to kind of keep on top of that and understand what's going on. So the first thing I wanted to pull out of the paper was like, what's the problem statement? What are they trying to actually solve? And the biggest thing is that you ask these large language models certain kinds of questions and it just can't do them because it doesn't understand the concept of the structure. So a lot of people say like, what page is this on, or what's the best, or what's the outcome of this table, or stuff like that. Can you summarize the key takeaways from this range of pages? There's people come in with a lot of questions like that, and the large language models fail to do that because it doesn't understand the concepts of this is a certain page or this is a table, or if you're using a retrieval system, it's not going to be able to accurately pull that out. It might, but in a lot of cases, it's not going to pull out the right context. So that's a problem statement. And then the typical approach that people have with these tasks, it's become popular to do RAG, retrieval augmented generation. And so this is this concept that you have your document and then you chunk it up into little pieces, and then you pull out the pieces that are relevant to the query that was asked. And so the way that this is done is you chunk your data, and then you pass it through an embedding model, and then that gives you a vector that represents kind of the meaning of that chunk. And then when a user brings in a query, they go into ChatGPT and they say, I want to know the revenue of the company in this table or something like that. It will go and it will try to find the most relevant chunk from the data, or multiple chunks. And then you pass that as extra data into the LLM. So instead of just asking the LLM directly, you give it that chunk of information, and then with that extra context is able to more accurately answer your questions. And so this approach can work sometimes in that kind of scenario. Like, for example, you might have like the page numbers at the bottom of the page, and then it might be able to pull out, oh, I see page number 5 on this, page number 6 on that, page number 7 on that. And it might be able to retrieve it, but it's also very likely that that isn't present, or even if that page 5 is at the bottom of the page, what if your table's at the top of the page and they're in different chunks? So it won't actually match up. So it's possible for RAG to do this, but it's very often not going to get the correct understanding of your query of, I want this specific table, or I want this page range, or I want just the header or something like that. So in this PDFTriage method, what they did is they basically gave the LLM a set of tools, and they said, have the LLM decide and interpret what the user wants. So it will take a question like summarize pages 5 through 7, and the LLM will take that and says, okay, I need pages 5 through 7. And then it goes and it calls this function fetch pages, and it says, give me pages 5 through 7 as my context. And then it's able to use that in order to do its generation and summarize that page range. And so with this, it's able to do all of these different tools that they've kind of coded in that it's able to interact with. So this is kind of the structure that they follow. They take a document and then they pass it to an API that will chunk it up. So you start with your document and it will split it into sections, and then it splits it up into, like, it turns it into HTML. So you have headers and paragraphs and bullet points and all of that stuff. And you can see that it shows the structure of the pages and the sections and the tables, etc. And then when you pass it to the model will output something like this, saying, okay, grab me pages 5, 6, 7. And then after that, it's passed into the LLM again, and it says what is the outcome after we retrieved those pages. And so walking through specifically how they do that, this step back here, they take a document and then they turn it into all of this stuff. That's kind of a challenge on its own. So what they do is they use this Adobe Extract API, and that's what turns their PDFs into this HTML-like form, and then they convert it to JSON, and then they convert it to Markdown. And I don't entirely understand why they have to go through that whole process, but I can actually show this is what the website looks like. And so if you want to, you can just pass your own documents through here and get a similar outcome. So you can see that if you click on the title, it shows you all of the stuff that's inside of it. And so this is kind of a interesting tool for anyone who's working with documents. Is pretty valuable to be able to get a structured output like this. So as far as evaluation, how they measured how good their approach actually was, they pulled 1,000 documents from Common Crawl, and then they sent those off to Mechanical Turk, and they just said, ask some questions about this. So they had a bunch of people look and say, what's a good question to ask of this document? And then they classified it into various different groupings. And so they kind of said, here's the different kinds of questions that we see people asking, and let's kind of pull out the best of the best. And then they took a subset of them. And then they actually use that as their evaluation. And so now what they're doing is they're comparing RAG against the PDFTriage. And so this is kind of the old approach, is like, let's just do an embedding and then try and pull back out the correct stuff. And you can see that the PDFTriage is the black line, doing page retrieval is the gray line, and then chunk retrieval is the white line. So most people end up, like, the default is kind of chunk retrieval, just saying, let's pull out 4 sentences or something like that. You can determine what exactly your chunk size is. But then they said, well, let's try doing it at the page level. So that problem that I was talking about, where if, like, page number 4 is only all the way at the bottom, but the chunk that you want is all the way at the top, they did full page retrieval. So they just pulled exactly the whole page that was relevant to this specific query. And so they ran it through both systems, and then they asked some additional annotators from Upwork, and they said, which do you prefer? And then they also had them rate it on a few different criteria. So is it accurate? Is it readable? And there was some third thing. And ultimately, they found that the PDFTriage was considerably better. It was preferred in most scenarios. Not as much as I would expect, given the questions that they were asking it, but it does actually show that the method works. So having the model use those tools in order to retrieve the correct context itself is actually quite strong. So that was first paper. I don't know if we want to pause. Any questions? Feel free to type it in the chat or unmute and ask if you have any. Yeah, Christian.
Hey, Ryan. Yeah, thanks for the overview. Very interesting papers. Actually, working with PDF documents, and I found there are no like robust open source tools to like extract the text. So I was wondering if have you encountered that problem before? It looks like that tool, Adobe, they made it, so they probably solved it. But do you have any recommendations?
That one looks good. I haven't specifically used it, so I can't verify its quality. Part of the problem, I mean, there's lots of different kinds of PDFs. You can have digital born ones that actually have the text embedded in them, and then you can have ones that are just scans, and so that kind of further complicates the problem. At my company, we've been using PyMu PDF, but that has a commercial license, and it might be difficult to get a hold of that. And then the other one that we've used is I've tried PyPDF and PyPDF and a few others, and they all work okay, but they're not great. They all have lots of failure cases where they'll render the text improperly and not be able to extract. PyMu PDF I've found is significantly better. That's at least, yeah. And there's good examples of extracting that text out. So yeah, if you're working with PDFs, that's where I would start. Yeah.
Okay, got it. Thanks.
So Ryan, would you say this is an example of the trend that just LLMs are very powerful? So you give it this structured format and then just basically tell it, go and get me what I want out of this data?
I think that ultimately all that's happening here is it's interpreting people's query and then it's translating it to get the right chunk out. And so I don't ultimately think that it's like some extreme skill of the model. It seems like a fairly basic interpretation of, okay, summarize this down into a query. But it is another application of like, well, quit having a human do it. Just let the LLM sit in there and do that for you. So in that regard, I do think that it's kind of LLM solves everything.
Seems like there's kind of a pattern of, if the LLM can't do it directly, like, maybe it's a complicated math problem, you tell the LLM, well, write a program that would do it and then run the program.
Yeah.
This reminds me a lot of that approach, which seems like it's, getting some great results.
Mm-hmm. Yeah, a lot of this is hinged on having the function calling from OpenAI, where it can basically say, okay, make the model call this tool. And so you give your model a whole bunch of tools in order to do various different things. And I think that's we'll see that more and more as the models will get better at using these tools instead of, like, right now their objective is really guess the next token. And I think we'll see better tuned models for using many different tools that powers them up even more.
Cool. Thanks, Ryan.
All right. So moving on, the next paper is all about segmentation. And so I figured I would just give a little primer on what segmentation even is. So segmentation is like, you might have classification saying, like, is there a dog in this picture or not? Segmentation is a level beyond that, saying where in this picture is the dog. And then you have to kind of draw out the whole map of all of the pixels where the dog actually is. And so you can imagine this is orders of magnitude harder than just saying, is a dog in the picture or not? You have to actually go there and draw a very detailed polygon potentially and paint it all in. So it can take a long time in order to do this. So if you want 10,000 labels for just regular image classification is probably cheaper than 1,000 segmentations. So data is typically very sparse on segmentation. You can't get a lot of labeling on it. And so this paper that we'll be looking at is all about how do you stretch those labels even further when you don't have very many. And so the paper that I kind of was looking at, I've been looking at all kinds of different pseudo-labeling stuff, but the one that we'll be looking at today is called pseudo-seg. And so the kind of basis of this is pseudo-labeling. In order to stretch the limited data that you have, you can do a process called pseudo-labeling, which is basically you take a model that's already been trained against the limited data that you already have, and then you go and you apply that to a big pool of unlabeled data. So say you have 1,000 images, but only 50 of them are labeled. You train against those 50, and then you run predictions against the rest of them, the rest of the 1,000. And then you can try and filter those or do something else in order to kind of pick out the best ones that your model did on. And then you can use that to retrain now that you have a slightly bigger data set that might be a little bit noisy, not quite perfect, but is probably better than only training on 50 pages or 50 images. And so this is kind of a way of just let's expand out our labels. And this can work for almost anything. Like it works for text and image and segmentation and whatever. A lot of people have used the general concept of pseudo-labeling in a lot of different stuff. It's just about data availability mostly. So pseudo-labeling is difficult because you're doing this at a pixel level. You're not doing it at a broad level. So it's kind of difficult to do that filtering step. With classification, you might be able to go and say, okay, which ones is the model very confident on? And then you can use that as a filter to then go through and just kind of verify yes, no, yes, no. It might have pretty good precision, and you can kind of just manually clean those up, or you can use it directly. But it's much harder when you're looking at the pixel level, because if you're at the pixel level, you kind of have to look at it much more deeply and say, is it tracing the line of this correctly? Is it accidentally pulling in an extra object as a dog? It's just much more tedious to actually do some correction and to filter things out. And so what they propose in this paper is a new single stage way to utilize the unlabeled data. And so what I mentioned earlier is you can have your base segmentation model that was trained against only 50, and then you go and you make predictions against the other 1,000, and then you can retrain based off of that. And you might be able to get some value out of it, but typically it's kind of difficult in order to extract much more value out of the segmentation when you've already trained the model against what you have available. And so what the paper is really doing is it's showing how do you create a more reliable pseudo-label. So they use GradCam, which could be a whole talk of its own. But it's basically this method where you can extract out and basically say, what is the model looking at in order to make its decisions? And so you can see it's used for a lot of other simple tasks like classification, where you can say, I've got this model that's trained on classifying cats and dogs, and then you wanted to actually say, okay, where is the cat, where is the dog? But you only have that like very coarse label. And so this is kind of a way of making the model or extracting out from the model what it's looking at. And so they basically said, why don't we use this as an additional signal as to what the model should be outputting? But you can see like this is the GradCam output, it's not very good. It's kind of just this region around the face, and it says this is mostly what it's looking at. And so they use this implementation that's kind of a level beyond it, self-guided attention GradCam, that gives them this more detailed look like this. And then this decoder output is the original, the prediction from the model that was trained on the initial 50 to start. And so what they've done is they basically said, let's take these two sources, the SGC map and the decoder, and let's find a good way to combine them. And then we can get a more reliable pseudo-label with the combination of those. And so that's kind of the gist of the paper is there a way to get a more reliable pseudo-label versus just making the prediction directly? And so their results are really good. You can actually see that they compare against just training a supervised model versus their method. So you can see when they only have a 16th of the label data available to train against, it gets like 55% MIOU. But with their method, they're able to get like above 70%. And so it's kind of incredible that if you look at this, this is with 1/16 of the data, you're getting the performance of 1/4 of the data. So you have to annotate 4 times less data in order to get the same performance, which at times can be a huge time saving if the annotation is actually expensive to do. So I feel like this is a metric that more people should be looking at and understanding, is like, how do you get equivalent performance for less data? That's something that I've been looking a lot at in my current work, is how much better can we do with less data? And so in this table down here, they show how the model does when it's retrained just on its own output. So the decoder only, and then here's the SGC only. So that's just using that self-guided GradCam. And then here's the combination. So you can see that there's a decent boost from using the combination of these, especially in the low data area. Just training on its own output or on that GradCam yields pretty bad performance. And then on the combination of them, they actually get significantly better reliability off of that. And then this last graph over here, what it's showing is the some people, when they do pseudo-labeling, they will choose some threshold, and they say it only counts as a positive if it's above this threshold, and it counts as a negative if it's below that threshold. And then you separate out the classes, and then you retrain based on that. But what they show in this paper is that that's pretty unanimously the wrong choice to make. If you make a thresholded decision, you're actually losing a lot of the information out of your model's prediction, because your model is giving you a sort of noisy estimate of its confidence. And when you threshold it, you're actually kind of just throwing away a lot of information. So the lines to really compare against is, so here's the soft at a quarter data. Here's the hard threshold at all of these different thresholds. And you can see that especially on the low data one, you can see that it gets above 70%. And when you start thresholding it, you lose a decent amount of the clarity there. So yeah, that's the 2 papers I have prepared. Any questions about the pseudo-seg?
Yeah, I had a question here. So my understanding of this is, say if you have like a medical, a patient, you're trying to get an image, you have reconstruction algorithm. Now, one of the further steps in image processing is just segmentation. And then once you have all this set, then you have classification. Now, where are you talking for segmentation for auto labeling? Is it still in this image formation stage, or is it more like classification?
Depending on how it's formulated, this can actually be both at the same time. So it will be able to tell for a given pixel what class it is on top of what what the shape is. So it's not purely a shape thing, actually. So like if you look at this one, these different colors represent different classes. So like this one up here is a dog, and this one down here is a cat, and it's represented as different classes. So in medical, it would probably be similar, where you say, okay, this is kidney, and this is some other organ, or this is cancer, and this is non-cancer. And it can draw the outline, but it also tells you the class of what it is.
Okay, and then I appreciate the comments, Ted. And then, is this the same thing as object detection?
It's related, but it's not quite the same thing. This is more granular than object detection. Object detection is just a bounding box saying there's something in this region, and the segmentation is like at a pixel level. Every single pixel gets classified as a different class.
Okay, so the term is technically labeling segmentation, correct? Because segmentation is just slicing.
So in computer vision, there are actually a number of different terms. I think the most common ones I've heard are semantic segmentation, instance segmentation, and then oh gosh, I can't remember. But basically, it's like in the one you say this pixel is dog, okay? And if you have 3 dogs and they're kind of overlapping, you just get one thing that says all of this is dog. Okay, and then in instance segmentation, you get dog 1, dog 2, dog 3. Okay, so you have to uniquely identify each instance of a particular class. And then I don't really quite understand it, but basically the most detailed, the hardest one is what they call panoptic segmentation. And what that means is then you cannot have any overlap between objects. So every pixel has to be exactly only one thing. And so it means that you really need to get right which thing is in front of what thing. And so you have like a person riding a bicycle, like there's their leg. And so like every pixel is either part of the person or it's part of the bicycle. Like, and that's the level of detail you got to get right if you do panoptic segmentation.
Okay, thank you.
There's a question about what motivated the authors to make use of GradCam. I feel like it's a somewhat known method to try and get segmentation maps out of models that were kind of weakly or data that was weakly labeled. So a lot of people will actually try to get segmentation output from something that was only really trained as a classifier. So people will take something that was like trained on ImageNet to classify 1,000 different classes, and then they go and they apply GradCam to it, and they say, can I make it highlight where it's looking at in order for those classifications? So I've seen a lot of people use GradCam for that purpose, and that's probably where it came from.
I don't know if this is too much for this 1 hour session, but can you give a little bit more detail on how GradCam actually works? And I'm thinking, is that technique applicable to things that are non-visual as well?
You can use it for pretty much anything, but it's much, I mean, I don't know how you would interpret stuff that comes out of like a text model or something like that. I think that would be difficult to do. But I mean, it can theoretically be applied to other things. It's just without an image to go look at after. I don't really know what you would be able to explain out of it.
Yeah, so like my super short explanation, Kirk, would be that let's say you have a CNN that you're using for a computer vision model, then people assume that there is a correspondence between the locations in your CNN feature maps as with the original image.
Okay.
So let's say you have a feature map at a certain part of the CNN that's 32 by 32, right? Then they would basically say that each of those long vectors with, you know, many channels corresponds to 1/32 of your original image with the corresponding positions. So the upper left
Okay.
corner of the feature map corresponds to the upper left corner of your original picture. So what
Okay.
GradCam does is it looks at the largest activation values, and it says that's where this whatever neuron is highly activated, and so then that gets the brightest colors in your GradCam. So like what
Okay.
Ryan's showing right now, I think
Yeah,
red
yeah.
is the brightest color, and so red corresponds to large activations on some feature map inside the CNN.
Okay, so you'd almost have to have data that was put in some kind of a, you know, a 2x2 matrix like an image, or, you know, a two-dimensional matrix like an image to have that technique work.
Yeah, and I can't remember, but people have used GradCam for other things, but what you don't get necessarily is the correspondence between this intermediate representation and this part of my original input.
Okay.
So you can say, here's the GradCam that says, oh, node 1 was highly activated and node 17 was highly activated, but what does that really mean? Whereas when you use the CNN, you can say, oh, well, node 1 corresponds to the upper left corner, node 17
Gotcha.
corresponds
Okay.
to the, you know.
Yeah, I was thinking about something like if you wanted to take, you know, like a whole bunch of pieces of software and classify them as to their function, like could you use some technique like this to better understand what the software was doing? But you'd have to find a way to put it into a form that it could be used this way, which might be a pretty big challenge.
Yeah, like super simplistically, if you have any kind of classifier, GradCam will tell you what part of the input was highly created large activations, which implies that it led to. Technically, large activations don't have to lead to, but that's what people do.
Yeah, like in the example of a software classifier, certain lines of code are going to be more important to what the function of that software is than other lines. And maybe you could use some similar kind of technique to kind of tease out what's actually defining what the software does. And
Yep.
you know, just as an example.
Yeah, you just need to find a way to map it to your inputs.
Okay.
Which again is much easier in a CNN.
Yeah. Yep. Cool. Thank you.
Yeah, thanks for the question. All right, so I'll get started in a second here. I just want to say that Ryan and I talked about reducing this meetup to an hour to be a little bit more friendly to people who have busy weekends. and I know that I am not going to finish by 1 o'clock. I'll try to get closer. All right. So the first paper I wanted to talk about is this is Textbooks Are All You Need 2 paper. And so really to understand this, I'm actually going to talk about the first paper, Textbooks Are All You Need also. So this is a paper out of Microsoft Research. Okay. And they had Phi-1, which was the first LLM that they built. And these are very small language models, small in the modern sense. Okay. So like, you know, 7 billion is the smallest publicly available llama, I believe. And this is only 1.3 billion parameters. And this is a GPT style decoder only LLM, autoregressive. So like most of the open source, most of the things talked about today, right? ChatGPT, Llama, Vicuna, all of these are decoder only models. And to skip to the bottom line, by using very high quality data, they were able to get performance that was similar to much bigger models that are 5 times or 10 times bigger. Okay. And in this paper, they really worked on complex reasoning tasks. So these are very challenging, even for, you know, GPT-4. You know, complex reasoning is still pretty challenging. There's other things, right? Like it does better on certain factual information. It can pass whatever, right? The medical exam, the law school exam, you know, those things. But reasoning is still a challenge. So that's why they want to tackle that. So how do they get there? Okay, so first let's go back to Phi 1. Okay, so both of these papers came out this year. The first one was in June. And as I said, it's a 1.3 billion parameter model. This one, all they did was they said, we're going to test it on generating Python code. So the nice thing about generating code is that we have pretty concrete measurement for quality of that, right? When you start saying like, okay, I asked my my language model to write a poem, not as easy to say, well, my 1.3 billion model is how good compared to my 7 billion model, right? But if you're generating code, it's pretty black and white. Did the code work or not? All right. And what they did is they had, we'll get into the details of it, but they had 6 billion tokens of what they call textbook quality data. And then they had another 100 billion tokens that they generated. They did not scrape this stuff. And they synthetically generated some of it to be like textbook information, some of it to be exercises. So in terms of data quality, what's the problem out there? I'm not going to read through all this, but basically, if you just randomly look at code, there's going to be a lot of boilerplate code, a lot of like headers or whatever, and the examples might not really point to sort of like the algorithmic part where you're doing something, you know, like this is how I sort it. This is, you know, the loop that I use to do blah, blah, blah. All right. And so that's all valid code, but it's not necessarily very useful for training a model. So what they wanted to do was to get higher quality code examples. So for their code textbook that they called it, the pre-training data, they started with the Stack and Stack Overflow, and they filtered this where they basically built a classifier. I'll get into the next slide to say, is this a really high quality example that would be useful or not? Okay. And then the textbook set, they basically said, hey, ChatGPT 3.5, generate me a good example for someone learning to program. And then finally, for the code exercises, what they did was they said, here's like a function name, and then basically you're going to do the doc string, and then you're going to write the actual code for this function. So what did they do in order to get this high quality stuff? So Ryan talked about labeling, right? You could try and just hand pick, what did I say it was? 6 billion tokens worth of code. You could hand pick all of that, but that would be very, very time consuming. Okay, so what they did was they had annotators take 100,000 examples, and so they went to like, you know, Stack Overflow, and they pulled them out, and people would rate them. I don't know exactly how, but like rate them, you know, 1 to 10. How much educational value does this? Sorry, let me rephrase that. So they used GPT-4, not humans. They used GPT-4 to take these 100,000 examples and rate them, you know, on a scale of whatever, 1 to 10, for how much educational value does this particular code example have. So they reviewed it. They were happy with it. They said GPT-4 does a pretty good job deciding, like, is this something that would be very educational? So if it has a lot of boilerplate code defining constants, that's not that educational. It's valid code, but it's not educational. Then they trained a random forest to basically decide which are the high educational value ones, which are not. So they ran that on 35 million examples, and they ended up keeping about 15%. So about 5/6 of the stuff they scraped, they threw away, and they kept about a 6, saying this is high quality stuff. Now, the challenging part with the synthetic code examples is not generating high quality examples. That's actually relatively easy. What the authors cited is the difficulty with your synthetic examples is how do you make them very diverse? So you want really good coverage. So if all of your examples only show how to write loops and nested loops, then you're going to be missing out on other topics. I don't know what topics, hash tables or other kinds of topics, right? And so they looked at another paper that had done regular natural language generation, and in order to get diversity, what they did was they said, we're going to build a list of words and we're going to randomly select words from this list, and each time when we do a generation, we're going to say you have to include these whatever 5 words. Okay. And so that then pushed it to make sure it was generating diverse things, because it was having to include whatever those different words that you were pulling out from your list. So they did a similar thing, except instead of just words, they did topics. Okay, so they had programming topics, and they would say, give me an example, and the example has to address this topic. And so then hopefully that forced it to give you a very diverse set of code examples. And I don't fully understand this, but then for the code exercises, basically how they got diversity is they would generate very diverse function names. Okay, and so the model's pretty good at having the actual function correspond to the name. And so if the function name was sort a list, then it would write a sorting function, right? If the function name was whatever, build a search tree, then it would, so by giving it a very diverse set of function names, then the code examples that it built would be very diverse. All right, so how did it do? It did very well. So the yellow highlights are mine, not the author's. You'll see GPT-4 in the middle, okay? However ginormous that is, okay? Yes, it did the best on this human eval benchmark. Human eval is a coding benchmark. Wouldn't necessarily guess that from the name. And what they're using is whether or not the code was valid using only one try. So that's the pass at one. But other than that, you'll see down at the bottom, Wizard Coder did pretty well. And that is a 16 billion parameter model that was trained on 1 trillion tokens. But this Phi-1, much, much smaller than most of these other models, only 1.3 billion, only trained on 7 billion tokens. It got similar score, 50%. And this 50.6% on human eval beat all these other models. And if you look on here, you'll see there's 12, 13 billion parameter models. There's GPT 3.5, which is somewhere over 175 billion. It's not specific to coding, right? But so it did really, really well. And then this MBPP, I forget exactly what it stands for, but basic Python programming, something like that. Not all these papers have comparisons, but you can also see that Phi-1 was very competitive with that. So they did a small ablation to say what contributed to the really good code generation quality. And there's a couple things that they're looking at here. Is they're looking at the data that they used, the model size, the number of tokens. So everything helped, but whether they did a 350 million parameter model or one that's 4 times bigger, 1.3 billion, it was a modest improvement. Okay. What really made the biggest difference was this fine-tuning that they did on the code exercises. So brown is just sort of like scraped examples. Light blue is when they had their curated stuff, where they auto-generated an additional set of tokens, right? And then this dark blue is when they further fine-tune the model using their code exercises. So this is something that we've seen elsewhere, right? Where if you have a specific problem If you take a small model like Llama and you fine tune it on really good examples for what your problem is, you can beat the general performance of a big model. You can beat GPT 3.5. You can sometimes beat GPT 4. It won't beat it on everything, but it'll beat it on your one task. So the conclusion with Phi-1 is that, yes, you can have a much smaller model, much less data, you can get really high quality, but this isn't a completely general thing because Phi-1, it only does Python, it doesn't do all languages, it only knows the most common packages, and it's kind of brittle. They said if you made grammatical mistakes in your prompt, it could break it. So this is really just sort of a proof point that high quality data matters, not that this itself is the final solution, the end all be all. So once they did that, then they wanted to build on that, and they said that was great for coding, but let's again go and look at common sense reasoning. Okay, so they use the exact same architecture as Phi-1, 1.3 billion decoder only, and they added a lot of data to it. So we had 7 billion tokens. Now they added another 20 billion tokens to do common sense reasoning, multi-step reasoning, that kind of a thing. And they had this alternate data set where they filtered a bunch of stuff from the web. Okay, so they had synthetic data that they thought was high quality. They had filtered web data they thought that was high quality. And then just to note, none of these models were instruction tuned. They're not chatbots. They're just regular completion LLMs. So in the end, when they trained on all of this high quality data, it did really well. So you may not know all of these benchmarks, Winogrand and these others, but basically what you would call sort of common sense reasoning, this is sort of one-step reasoning. All of these models did pretty well, and their Phi 1.5 did pretty well. One thing I'll get back to, but you'll notice, is that the Phi 1.5 web seemed to do better than the Phi 1.5 in general. And then this is language understanding and knowledge. So if you're familiar with MMLU, OpenBook QA, Squad, HelloSwag, again, they had pretty good performance. Not as good as some of these bigger models, but pretty strong performance. Once again, I felt like the overall, the Phi 1.5 web tended to do better. Whoops. And then this last one is the key one here. So they called it multi-step reasoning, but if you're familiar with GSM-8K, this is grade school math. And this is one that LLMs all still really struggle with. Okay, so you can see that Llama 65 billion was able to get half of them right. Okay, they got pretty close. They got 44.6 and 40.2%. But they did really well on the coding tasks, the human eval and the basic Python programming. So I don't know if I would call this close. They got 41%, whereas Phi-1 got 50%. On MBPP, they got 43 instead of 55. So basically, it's true that they didn't suffer like catastrophically worse Python programming. Because remember, now the training data is only 1/5 Python. Okay, something like that. Whereas before it was 100% training was Python programming. So it did suffer a little, but it didn't suffer catastrophically. So now it can do really well on this and still do quite well. Still beat a lot of other bigger models on the programming tasks. So in conclusion, basically they say, hey, reasoning is one of the hardest things, and we think that this further supports the case that the quality of data, not just the quantity, really matters when you're talking about language model performance. And so you can train it to do more than one thing, so it doesn't have to be uber specialized to do just one thing. So anyway, I just wanted to I thought this paper was interesting because what we saw was this trend, right? GPT-2, GPT-3, I can't remember all the models that were just getting bigger and bigger and bigger, right? And so it was all about large model size. And then we had the chinchilla paper, and it's like, well, hold on a second here. Yes, your models are bigger, and in general, a bigger model will do a little better. But unless you have a lot of data, you're only going to get marginal improvement from a bigger model. So if all you have is, and I say all you have is 1 trillion tokens to train it on, then if you keep making your models bigger and bigger, you're really not going to get much performance improvement if you train it on that same data. The reason why, as people were building bigger models, the performance kept moving up more than just a teeny bit is because each time they did that, they were also giving it more data. And so the chinchilla paper looked at like, well, we can look at compute optimal, and maybe, you know, in order to get a certain quality, you actually don't need this ginormous model. So that was sort of the first big change. The second movement in LLMs was, oh, it's not just model size and parameters, it's data size. The third movement now is it's not just data size, it's data quality. So if you scrape the internet and you just have a lot of bad text with grammatical mistakes and slang and typos and all that kind of stuff, you're teaching your LLMs that. And so ultimately, for us to be able to have models that fit on our phone or whatever, that are not ginormous models, we may need to kind of look at how do we get really high quality data on these smaller models. And then I do have references here. So the Kaplan paper talks about scaling laws when they were just trying to make models bigger and bigger. But then the second one is the chinchilla paper. And then not as much, but the Llama and Llama 2 papers talk a little bit about how smaller models can compete with what used to be just the big models. All right, any questions? Question in the chat about educational value of the code. So no, they use GPT-4 to rate the educational value, and they found that they thought it did a good job, so then that's what they went with.
I wonder about the reasoning. Did they make a distinction between pure math logic reasoning and quite common fuzzy reasoning, which people use in their life?
Yeah, I don't know a lot of the details, but I will say that I do think that a lot of our benchmarks for language models are not the strongest. So that's why I put in quotes what the category was: language understanding and knowledge. So that's what it's labeled, but take it with a grain of salt whether or not that's really what exactly we're testing with these benchmarks. So it's you know, I think the movement now is if you're building a small model, you can do something like use GPT-4 to compare it and rate it. And if GPT-4 says you did a little bit better, then your model probably is a little bit better. But if you're trying to build a model that's better than GPT-4, I don't know how you're going to measure it, because just some model like MMLU, and now they have bigger ones, Big Bench, whatever. It's, you know, it's debatable, and it's different tasks, and so we do not have a great way of measuring how good these models are.
Now, did they tend to report things such as, you know, weight decay or the precision of the weights that they use?
Yes, it's in the paper. I didn't go into a lot of those details, so there's some pretty standard things. Where's the paper? If you look in the paper, they give the architecture, and it's pretty standard things. You know, they use flash attention. In this case, the original attention has like sequential attention and feed forward networks, and they use parallel ones, which speeds things up a little bit. They do list like the learning rate and training and all that stuff, but There's nothing, I didn't see anything too special in the architecture. It's just pretty much like the I think I passed it. The standard tools of the trade these days. Not necessarily the same thing people were doing a few years ago, but pretty standard.
Now, what would you guess is the precision of weights that they use? To how many decimal points?
I'm gonna guess that they use standard mixed precision, so some form of 16-bit float. I still see a lot of float 16, although people are moving to B float. I think it just depends on whether you're like whatever, Google camp or a Meta camp, whatever, whether your historical code base that you're building on was using one or the other, And then I think generally people are using full 32-bit float precision for things like gradients and things like that when they train these models.
Okay, thank you.
Seems like the on that graph that you have up there right now, the state of the art in multi-step reasoning is still not very good. Do you have a sense of where it goes wrong, and why would just making the quality of the input data have such a pronounced effect on multi-step reasoning as opposed to some of the other ones?
So language models are not very good at it. But just to be clear, you notice they're not comparing themselves to GPT-4 on here. Okay. I think GPT-4 gets like 75% or somewhere around there. Okay. But that's still not that great when you consider, I mean, this is grade school word problems. So, Sally makes $5 an hour and works 3 hours on Monday and 6 hours on Tuesday. How much money did Sally make? This is not exactly like world beating. Maya talks about like solving math proofs and things like that. This is just like, can you do 2 or 3 arithmetic operations in a row? And they're not doing that great. So then
is the breakdown between like if you broke those things out into separate problems, it would probably do fine on each of them, right? Is the problem in chaining them together, or?
Yeah, that's why the multi-step reasoning. So I don't think they necessarily did chain of thought prompting or anything like that for this particular thing. But what you can see here is they've got some of these models, these 7 billion parameter models, that do poorly on GSM-8K. And then these even smaller models just bombed, where they actually did worse than random guessing. So they're saying that, hey, our model is as small as these, but you can see it did way, way, way better than random guessing. I'm not 100% sure what this via coding means.
So why would the quality of the data have so much an impact on that, as opposed to the size of the model or the number of examples or whatever else you could?
Yeah, that's basically exactly why I picked this paper, is because again, different people have different interpretations, but if you're just doing next token prediction, okay, if you think of it, that's all it's doing. Then I may say I'm not hungry, or I may say I ain't hungry, or I may say whatever, right? And if you see all of that in your training corpus, then you will, with certain probability, output all of those things. If you only want your language model to output whatever we call like standard academic English, then you really ought to only train it on standard academic English.
Okay.
And if you want to train it on accurate Python programs, if you just scrape GitHub, there's like buggy code on there. There's inaccurate code on there. So you are giving it a certain percentage of not what you want in your training data. So you wouldn't typically do this, right? If you were training a model to predict housing prices, you wouldn't expect 10% of all of the training data set to be like invalid housing prices. That's something that we would right away red flag. But to a certain extent, language models have some of that just because, you trained it on Reddit and Twitter and whatever, and it just has all sorts of garbage in there.
Garbage. Okay. Interesting.
All right. Any other questions?
Was there a specific reason why they chose this number of parameters? Is this thought to be like a sweet spot for something?
I don't know, and I don't know if Ryan, if you know, but you'll see that there's quite a few people who have gravitated towards this sort of 7 billion and 1 and change billion sizes.
I think it's mostly just the scale that you can fit reasonably in a single system.
Oh,
That's,
What do you mean, like how many GPUs?
yeah.
Yeah,
So like a 24 gig
like,
GPU.
Yeah, you can probably fit it in eight 48 gigabyte GPUs and then train that at a set precision. That's typically like the trade-off that people are making is like here's what you can do with a single system, here's what you can do when you scale to multiple systems. And most people play at the scale of single very strong system because it turns into a bunch of headaches when you start getting distributed.
Thank you.
All right, thanks. All right, so we're over. I'd like to do this next paper because I think this is just a really cool paper. And then maybe we won't have time for the last one. The last one's really short. So this paper's called 3D Gaussian splatting for real-time radiance field rendering. And if you don't know anything about this particular domain, there's like a whole lot of words in this title that are just like, what the heck is what? But they all have relatively simple explanations when you dissect it. So one of the reasons why I like this paper is because I just love the word splatting. I feel like I can't say that word enough times. It just makes me smile every time. But it's actually a really, really good paper, a really cool concept. So here's the problem that we're solving, okay? So you're going to get a sparse set of camera views, say, I don't know, 10, okay? A number of camera views of a scene. And you basically want to construct a 3D scene representation that allows you to generate new images from any camera angle that you want. Okay, so it could just be a 360 circle around the thing. Okay, now this is not to be confused with technology that basically just like interpolates between two images. Okay, so I think like when they made the Matrix movie, they had like whatever 200 cameras all in a circle. And so you could sort of interpolate between adjacent camera angles, and the quality would be high enough that you wouldn't really notice it. And so you could look like you could just smoothly. But this is actually talking about many fewer camera angles. So the big breakthrough, if you're not familiar, was the Mildenhall paper out of Berkeley. And it was called NERF for neural radiance fields. And so what that paper does is it just divides up the space of your scene into voxels. So just a big giant 3D grid, okay? And long story short, it would use a neural network in order to estimate the color and amount of what they use the term radiance, whether something is transparent or something's opaque. The color and the amount of light that you would see from each one of these voxels. Okay, so I'm going to play a little bit of the video. I'm not going to play the whole thing, just to give you like the big picture view of this. Oh, can you guys hear that? No,
I don't think so.
no,
don't.
I just realized I forgot to share. Hold on a second.
We present neural radiance fields, or NERF, a new method for representing complex scenes that achieves state-of-the-art results for view synthesis. Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation of the scene as a vector-valued function, which is defined for any continuous 5D coordinate, consisting of a location and view direction. We parameterize this scene representation as a fully connected deep network that takes each single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We can then use techniques from volume rendering to composite these values along a camera array to render any pixel. This rendering is fully differentiable, so we are able to optimize this scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images.
Oops,
So you
that's
think you
not
know
what I
Wix,
wanted.
but do you really?
Sorry. Go
We
back.
first show comparison.
All right. So that was just a little bit. So basically, that's the idea, is that from any camera angle, you have rays coming out of the camera, and what you see must be a sum of all the pixels, voxels, between your camera and ultimately where you hit something solid, if there's something you can't see through. Okay. So you divide up this space into 3D voxels that are uniform in size, they're uniformly spaced, and each voxel has a single RGB color and a level of density or opacity. So you can imagine, like, most voxels are just going to be air. There's going to be, like, they're just see-through, right? But if you look at, like, the Lego bulldozer or whatever, at some point when you hit that, the wall of the bulldozer is yellow and it's metal. It's completely opaque. You can't see through it. So then whatever's behind that doesn't matter. Okay, as soon as you get to like 100% density, then you're not going to see through it, and you don't have to. And then you basically just sum up all the contributions from all the voxels that are on the ray path from your camera to each of the points. So if your image is 256 by 256, you have 256 by 256 rays, and each of them you need to add up the contribution from each voxel. Okay, and the contributions from the voxels could be exact, but in this case they're not. We're using a neural network to approximate it. Okay, and so that's where the neural networks come in, because if you had, I don't know, thousands of camera angles, you might be able to have like this fully determined thing where you solve some linear algebra problem and you figure out what's the, color and density of every voxel. But you don't have enough information if it's a sparse set of camera views. So what you do is use the neural network, and the neural network has to interpolate and figure out, well, what should I do for places where I don't really have complete information? So if some of you aren't familiar, basically Radiance fields is like an entire field of machine learning right now. There's been a gazillion papers. I can't possibly keep up with them, but there's ones that deal with higher resolution and faster. And what do you do if something can have like reflections on it? You have like a vase and the sun's shining on it, and you're going to get highlights, right? Like all sorts of things that are built on top of the original basic nerf. So what this paper does with the 3D Gaussian splatting, instead of having square uniform voxels, okay, now what it's doing is it's using Gaussian distributions. So 1D Gaussian you're used to seeing as a bell curve. A 2D Gaussian, you can think of it as sort of like concentric ellipses with higher density in the middle and lower density on the outside. So a 3D Gaussian would be like concentric ellipsoids with the highest density on the inside and then lower and lower density as you get farther out from that ellipsoid. Okay, so they're using 3D Gaussians instead of the voxels. The other thing that they do is that the voxels are just a little square, a little cube, okay? These Gaussians can differ in size, and they can also differ in orientation. And not only that, but in this model, they can differ in their spacing. So the NeRF model is basically a grid-based technique. The 3D Gaussian splatting is basically a point-based technique. So it's built off of a point cloud, or in this case, it's not really points, they're Gaussians. So a very different approach, okay? So now you can imagine that in a scene where you have like a lot of just air, you don't have to assign Gaussians to those locations. And if you have something like the side door of a car that's like very uniform in color, you don't need a lot of detail there. But if you have something like the grille of the car or something else that has a lot of details, then you want more information there. And that's what this model is able to do, is it's able to dynamically allocate more information into regions with a lot of detail and less in regions without much detail. When you need to render this, it's somewhat similar to NeRF in that what you'll do is you look at your camera, you'll look at the rays coming out of it, and you'll sum all the information along those rays. It's just that now, instead of going through a fairly predictable set of voxels, you're going to go through a certain number of these Gaussians, and you have to in some way quickly determine which Gaussians you want to contribute to this ray and which ones have so little contribution that you're not going to bother. All right, so that's setting the scene for this. Any questions before I kind of go on a little bit more into the details? Okay, so not going to be able to get into all the details how they do this, but basically there's this technology known as structure from motion. You may have seen this where people have like do this with video, but basically if you compare two different camera angles, structure from motion will sort of find the same point that is in both pictures. Okay, and from that, sort of with the parallax, it can kind of determine how far it is from you, and ultimately it can kind of build a 3D model of key points. Okay, so structure from motion will give you a 3D point cloud. So you could give it a series of still photos. You have to tell exactly where the cameras are, or you could actually use a video where the camera is just like moving through, panning around, and so there's a certain amount of delta between, you know, adjacent frames. So so that's known technology that the authors didn't need to do anything with. Use structure from motion. Okay. Then for each of those points, they assign a Gaussian, and you start out with something fairly straightforward. Then they're gonna do backpropagation. So just to be clear, when you're talking about NeRFs and you're talking about this, we're going to take a neural network and we're going to train it on this one scene. Okay, so this isn't the case where you have like a generic reusable model. So when you train an image classifier that does dogs and cats, once you've trained it once, you can give it multiple images and it'll say, oh, that's a dog. Oh, I think that's a cat, whatever. In this case, no, you train from scratch for every scene, and you can't use that neural network for anything else other than that scene. All right, so we're going to run an optimization where we train the neural network weights. Okay, so we want them to understand this. So in this case, for each of these Gaussian, we're going to store a lot more information than we did in a NeRF. We're going to store the 3D position. That's sort of the same as a NeRF. We're going to store this alpha. That's the opacity. That's the same as a NeRF. But then in addition to that, we're now going to have anisotropic covariance, which means that this ellipsoid can be oriented any which way in 3D. Okay, if it were isotropic, it would just be a sphere. Okay, it would be the same in all directions. It can be longer in some directions, and the long axis of the ellipsoid can be pointed not only X, Y, and Z, but also any diagonal in between. Okay, so typically a covariance matrix for 3D has 9 entries, but they use a trick where they actually use 7 floats to store this. And then they use spherical harmonics, which I had to look up. I wasn't familiar. There's a little picture in the lower right corner, but basically spherical harmonics are a basis function for spheres. And so if you take the first 3 spherical harmonics, then you have 9 different values, because there's the 0th, there's 3 first order, and there's 5 third order. It's the same thing that leads to, I believe, the like orbitals for electrons in an atom. So if you're into that sort of stuff, spherical harmonics. Anyway, so what this means is that in NeRFs, the voxel just gets assigned one color. That's it. How transparent is it? And it's one RGB color, 3 floats. In this case, each of these Gaussians can be like redder on one side and bluer on the other and whatnot. And so the same portion of space can look different colors from a different direction. So this takes into account that, like, if you have the sun or you have light shining on something and there's a highlight, a reflection, glare, whatever, then things might be much brighter from that direction, but not from other directions. And it can be trained on all of this. So it's a lot more data. And so then once you basically do back propagation, where you say represent the scene, now go and render it, and I'm going to look at the error. How close was your the picture that you rendered to the actual, and based on that, I'm going to run back propagation. Okay. When it comes to the rendering, it's this slightly more complicated process where they break the image into small tiles. They say which Gaussians are along the path of that tile. They splat each 3D Gaussian, these ellipsoids, onto a 2D plane. They sort those 2D planes by how far they are from the camera, and then they do the basic thing that we've been talking about, where you sum up the light contribution, the color contributions of each one, from the front closest to the camera to the back. In this case, it may sound like this is a complicated thing to do this splatting and summing, but this is techniques that already are being done in computer animation, and so it's very fast. They can take advantage of existing techniques. So one of the key things is this optimization that they do. So when they backpropagate the loss function, it's a combination of just L1 reconstruction loss, how close are the generated pixels to what the ground truth was, and then they also have this structural similarity metric that they use. And so SSIM is like other image loss functions, but it is calibrated based on human perception. Okay, so there are certain things that the human eye, the human brain notices more, and certain things that the human brain notices less. And so what this does, rather than penalize everything equally, it penalizes based on what people are likely to notice. So this is a very human-oriented loss as opposed to a more arbitrary fair judge on, like the difference. So they warm up this thing. There's some details there, and each pass they're going and they're back propagating in order to adjust the weights in order to get the picture to look more like the real thing. But every 100 iterations, what they do is they say, I'm going to look to see where there are large positional gradients, and if something is under reconstructed, which is the top row of the image, then that means that I need more coverage. So I'm going to clone my Gaussian, and I'm going to create 2 Gaussians, and I'm going to keep optimizing them until they sort of fill up the region like it's supposed to. If I'm over reconstructed, we have the bottom line. And so if we have one big Gaussian, what I'm going to do is I'm going to split it into 2 smaller Gaussians so that they can then orient themselves and better fill up the space. So they do that not every pass. They do that every 100 passes. And then one problem with all of these techniques, I don't know why, but you get these floaters. So where it should just be air and there should be nothing, you actually get fuzziness in the picture. And so to fight that common problem, every 3,000 iterations, they do this thing where they dramatically lower the density of everything. And then they run an optimization step, which should raise the density back up. Okay. But if you're in a region that really should be clear and have no density, then it won't. And so then what they do is they have a hyperparameter, they have an epsilon, and anything that the density is less than that, they just delete, throw away the Gaussian. So the rasterization has some details, but basically they break up the image into 16 by 16 tiles. And I'm not exactly sure how they do it, but basically they estimate which of the 3D Gaussians are along the path of that 16 by 16 tile. Okay. If a Gaussian is very far away, it's going to have very little contribution to the color, and so that they don't consider it. They only want to consider the ones that are very close. So they've got a list of Gaussians that appear for each tile, and this is where they assign it a key based on how far it is from the camera. And there's apparently a GPU radix sort that's available on NVIDIA GPUs. And so it's this really, really fast sort so that they can sort all of these to see which is the closest to the camera, which is the farthest. And then this is where they have their custom CUDA code, where they basically launch a thread block for each tile, and they start working on each pixel, and they start closest to the camera, working their way back. And once they've gotten very close to 100% density, then they stop, because once you get to 100%, then you aren't going to be able to see behind that. So that's the rendering process. And then when they're doing optimization, my understanding is they're not using AutoGrad. So they are manually computing the gradients, because AutoGrad would consume a lot of memory. And so they have some tricks that they do where they then basically walk those Gaussians from the back to the front, computing all the gradients so that they can update the weights to the neural network. And that's basically the gist of it. So it generates some very high quality images. You can see here an example of this train on the left. If they only run 7,000 optimization iterations, this is supposed to be blue sky with some clouds, but you have sort of this gray fuzz here. That's not part of the real image. And then this backyard scene actually looks really good, even only at 7,000 iterations. I have a link to the blog and the video. You can see they have a lot of really cool images. And if you look at this train, for example, there's this grill over here that's somewhat dense. And then even up here, it's even more detail, high frequency detail. And something like a NERF, because it's evenly spaced voxels, would only assign a certain amount of data to this region. But this technique can assign more and more Gaussians into this region, more and more smaller and smaller Gaussians, until it fairly faithfully captures what this portion looks like. I have a few numbers to show, but basically the gist is theirs here is at the bottom. The colors show the ones that do really well. So it does well on the structural similarity measure. It does well on signal to noise ratio, and it does well on perceptual loss. If you look here, you'll see that this thing was trained in 6 minutes to run 7,000 iterations, 41 minutes to do 30,000 iterations. You can see some of these fast models that aren't very high quality take similar amounts of time, 25 minutes, 7 minutes, but this high quality MNERF, MIPNERF took 2 days instead of 41 minutes to train. And so when you're rendering, that model can do 0.06 frames per second. So it takes like whatever, 15 seconds per frame. And this model here can do 134 frames per second at 1080p. So one downside, however, is I showed you all the things that it's storing for each Gaussian, and there's like 1 million Gaussians in a standard image. So this thing is like 734 megabytes of storage in order to capture all the Gaussians. They did ablations saying which part of our technique, not going to go into too much detail, but basically cloning small Gaussians, splitting them, was not very important. The spherical harmonics were not that important. So if they just had uniform colored Gaussians, that wouldn't have hurt it too much. But things that were really important was that if they put a cap on the number of Gaussians, that was really, really damaging. If they didn't use structure from motion to get the point cloud and they just did kind of like a random set of points, that was fairly damaging. And the Gaussian splitting. So when you have a Gaussian that's too big, splitting into two smaller ones was a very important technique for image quality. All right. So so basically state-of-the-art image quality for novel views. Training was basically the same or faster than other approaches. Ultra fast rendering, so that's why they put it in the title, that they can do real-time rendering. One downside is it requires more memory than NERF-based solutions. The authors say, hey, maybe there's some things you can do to kind of reduce the way the algorithm works, and we haven't really fully optimized the code. If you have some small number, like 10 camera angles, there still may be regions that are not well observed in any of them. And so this model, just like other NERFs and other models, is going to have challenges with doing that. They also mentioned something they call popping artifacts. I'm not really sure. I didn't have a chance to even look up what is a popping artifact. But then one thing I wanted to share is that both NERFs and this 3D Gaussian splatting, you are training a randomly initialized neural network from scratch on this one scene. So unlike an LLM, there's no pre-training. So these neural networks have no world knowledge that they've been pre-trained on. And so if you have something like a car and you have certain camera angles, it's possible that like something that had world knowledge would know something about the tires, the lights, the handles for opening the doors, like things that most cars look like, so that even if there was part of the car that you didn't observe, it could guess. These models cannot do that. Okay, the only input they have is the set of images that you give them, whether you give them stills or you give them frames from a video. So be interesting to see if someone can figure out a way to sort of add world knowledge to this, so that instead of it having to compute everything, if it can kind of infer what are reasonable and likely things to expect, and then it doesn't have to do as much horsepower computing. All right, way over time, so I'm going to stop here. Any questions?
So this seems like it's small enough and fast enough that in a few years we might be seeing, you might be looking at a video of a basketball game where there were cameras scattered around the arena, and being able to see almost in real time, like an instant replay of, from the basket's point of view, the ball coming toward you and hitting the.
Yeah. So apparently somebody has already written a plugin for the Unreal Engine.
Oh,
and so you can use 3D Gaussian splatting to create in real time 30-60 frames per second rotations of any scene. So if you Google on YouTube Unreal Engine 3D splatting, you'll see people have already done it. It's
wow, it's cool.
It's wild.
Do that.
Yeah. Any other questions?
So yeah, I had a question. I guess in all these papers, fully differentiable, deep learning, these types of things, how often are there comparisons to say like annealing or exhaustive exploration, these other types of things? Because we're kind of fixed on the deep learning. Like how close are the other methods?
Not quite sure how to answer your question because I could go very broad. I would say that like annealing, for example, generally speaking, is also working with something that is differentiable and continuous, right? It's just that maybe you're using a more cyclic approach as opposed to a one-shot straight line approach. But yes, one of the key things to this is that everything in your rendering process has to be differentiable if you're going to use backpropagation in order to train your weights. So in a NERF, they actually used a very simple, just fully connected. I don't remember what it was. It was a few layers. I don't know if it was 8 layers or whatever. Just regular old fully connected MLP neural network. Nothing fancy. And they're using that as a general function approximator. So it's a 5-number input and it outputs 4 numbers, R, G, B, and alpha. So that's basically the idea here because, again, if you had enough views, you could use linear algebra, you could figure out exactly what, each thing should be, but we're not doing that. We're using the neural network to have some continuity and have some approximations, some assumptions of the parts that are not fully determined.
Yeah, I'm just looking at the total number of shots with these or iterations. Would it make sense as compute gets better to start integrating these more compute hungry methods that might take less iterations?
Yeah, I don't know. I think that's going to be a case by case situation. So for example, if you look at diffusion text to image models, the original ones just did sort of very simple uniform steps in terms of the noise schedule. And now what people have figured out is like, oh, we can take bigger steps at the beginning, but then we need to take smaller steps at the end and blah, blah, blah. And so people have much more complex schedules. They're not cyclic like annealing, but nevertheless, along the lines of what you're saying is that like, yes, people are figuring out sort of schedules for these things. Not all gradient descent is created equal, I guess is one way I would say it.
Okay. Thank you.
There's a question in the chat. So like if you see a right side of the car, it won't know what the left side looks like. That's absolutely the case for both NERFs and Gaussian splatting. So typically you need, I don't know the exact number, but let's say like 8 camera angles sort of, around the object. That's still leaving a lot to be figured out. And so old techniques that just do interpolation, that just do sort of like smudging, blurring between camera angles, they can't work for that. And they definitely wouldn't work for so imagine you had 8 cameras that are sort of positioned around the outside. Maybe with some sort of smudging technique, you would be able to pan 360, and the quality wouldn't be that terrible. But with these techniques, you can actually fly through objects. So again, it depends on the quality of the representation. You might need a few more input camera angles in order to do that. But it's not just about. So I saw one, I can't remember what it was, where basically it was like they did a house. And so then you had a camera angle where it's basically like you flying through from the kitchen into the dining room, up the stairs, into the master bedroom, like able to do that kind of camera movement, not just like, hey, from the outside of a bulldozer or the outside of a park, let me just circle around it. So you really do need a better representation for that kind of thing. All right, I'll stop here. I can always save the last paper for December since we're so far over.
Thanks, Ed.
Thanks.
I always see the videos from NERFs and the Gaussian splatting, and I've always thought it was cool, but I've never taken enough time to actually look at it.
Yeah, it's very fun stuff, and I wanted to make sure to cover something different from like LLMs and whatnot. And who knows, like how at some point in the future this will apply to some other task, and we'll realize there's some convergence. All right.
Cool. Thank you
So,
both very
yeah,
much.
thanks.
This was super interesting.
Yeah, so I think we don't have too many people who joined late, but so we're hoping to do this regularly. December holidays, not 100% sure if we're going to do December, but Ryan and I will regularly talk about some ML papers that we think are interesting, and we invite you guys. You can do a similar, more in-depth presentation like we did, but like Ryan said at the beginning, if you just want to do 2 slides and just say, I saw this thing, I thought it was cool, we can have it just be a little bit more like lightning talks or whatever. But yes, we thought that'd be nice just to have this kind of event where it's just sort of keeping up with the news in terms of, it can be the latest, but it also could be that like you just ran across this paper, and even though the paper is 2 years old, it's the first time you ran across it, and that's totally fine. So just message Ryan or me. We'd be happy to kind of create like a sign-up sheet, and then we can just have sort of like monthly different talks about what people are reading and what people are seeing in the news. All right. So we were going to have office hours starting at 1 o'clock. So if you joined for that and you're very confused, I apologize. I think Ryan and I will take a little bit of time now to see if people do have questions so that you're not waiting until the next time we run office hours. So for any of you who want to stay for that, that's great. We'd love to have you. And if you're not, you can drop, and we'll shift gears now to the open question and answer session. Oh, and Ryan, you can probably stop the recording.